specializing in fault-tolerant quantum algorithms. She's the founder of Quantum Africa and an Arab Young Pioneers Award recipient. She's very passionate about open source education and building global quantum talent. Please join me to welcome Yousra.
Assalamu alaikum. Hello, everyone. Thank you so much for joining. My name is Yousra. I'm a PhD researcher at Niels Bohr Institute. I'm doing my PhD on quantum computing and quantum compilation, mostly interested in fault-tolerant quantum computing. And today, we'll finally be talking about quantum. So a lot of people here at the event are coming to me asking questions about quantum computing. Is it an easy field to start your journey in? And a lot of other questions. Yeah, so let me start by asking you a question. How many of you here in the audience knows about quantum computing? Okay, that's a small number. Yeah, so that's the purpose of the talk. And I really love giving this type of introductory talks in AI venues because we believe that the next generation of quantum computers is going to be designed by AI engineers. And it's just like an introduction for you to know that the field, it's true that it's complex, but it's not that hard for you to join and yeah, help us in building the next generation of quantum computers. Okay, to start, I'm not going to present this. I'm not going to show you about Schrödinger equations and these complex physics and quantum mechanics, but I'm going to take you in a journey where you're going to discover quantum computing from a really easy perspective, I would say. But before we dive into quantum computing, I just want to give you a small introduction about the history of quantum computing. So there was a really open debate in 1920 between two fathers of physics. One of them is Albert Einstein, who's the father of classical physics. And Albert Einstein always believed that quantum mechanics is incomplete. So quantum mechanics does not describe the whole reality or the full reality. From the other hand, there was another scientist called Niels Bohr, and he came with something called the Copenhagen interpretation. That means that quantum mechanics is a complete description of reality, and nothing in reality is actually there unless it's observed. And he actually proved this in one of his experiments, this experiment called the quantum entanglement. So you imagine that we have a zero angular momentum. You can imagine it as a particle or an electron. I guess you have taken some courses back in high school or undergrad about electrons and spins. So you can imagine if we do have two particles or two electrons that are governed by the same wave function, and I have one electron with me here. I don't know if it is a spin up or spin down, and since they are governed by the same wave function, basically, if the other electron is in another place in the world, the moment that I know the state of my electron, the electron that I have with me, and I can measure it and see the result of it, that it is a spin up, the other electron is instantly gonna reveal its information, and if we measure it, it's gonna be a spin down. We call this quantum entanglement. And this is a demonstration that the quantum information does travel faster than light. So this was his interpretation of the world, or the quantum world. And then in 1920, we had these three crazy scientists who came up with something called the ERP paradox. So they have proven that there is something called hidden variables, and quantum mechanics is actually a discrete, I would say, explanation of reality, because they proved that nothing can travel faster than light. And this has been the case. So for almost 40 years, everyone gave up on quantum mechanics, and everyone started reusing all the classical physics and the theories of Albert Einstein. Up until 1960, where a scientist called John Bell he came up with something called the Bell's inequality. And the Bell's inequality, so it's an experiment that you can read more about it in details, or you watch like some YouTube videos that explain it well. But he basically closed the gap, and he showed that actually information traveled faster than light. So he did the quantum entanglement experiment again, and he proved that particles are entangled. And actually, this is the reality, because everything in the world is entangled, and we're all like governed by one wave function. At the end of the day, we're all made of strings, right? And strings are energies. So when we talk about this, we talk about the computational advantage of having all these quantum theorems. So if we want actually to simulate or translate the correlation between only few hundreds of atoms in the universe, we will need as many bits as the number of visible atoms in the universe, because you cannot actually simulate or like isolate a system that it is entangled with the whole universe with its own wave function and study it by itself. You need to study the whole interaction with an open quantum system. And this is actually not feasible, so even with the best supercomputer or the best classical computer that exists out there, we cannot do it, and this is just unfeasible. Yeah, and from the other hand, when we talk about classical computing, we talk about Moore's law that says that the number of transistors on a microchip double every 2 years, and now the size of transistor on a microchip is 3 nanometer. So scientists are asking, can we actually make this smaller? Is it feasible or not? So this flagged the interest to explore a new paradigm of computing, which is inspired by the rules of quantum mechanics and quantum physics. And we ended up having something called quantum computers. So quantum physics and quantum mechanics is actually the study of atoms and particles at a very low fundamental level. And if we want to understand the quantum theorem easily, let's imagine that we have two players. One of them is called Anas, and the other is called Amin, and they are playing flip the coin game. So when they play this game on a classical computer that operates on the binary system only 0 and 1, we basically learned this in probabilistic classes or probability classes that there is an equal probability. So the probability of winning is equal to the probability of losing. And if you measure, you'll get like 50% chance to get a head and 50% chance to get a tail. But what will happen if we play this on a quantum computer? Does anyone have? Okay. Yes? Okay, yeah. So if we play this game on a quantum computer, we actually put our coin in a superposition. So the coin is going to be both head and tail at the same time. And we actually, once we measure and we output the probability distribution, we will end up with unequal probabilities. So the probability of losing might be bigger or less than the probability of winning. And this is actually the reality, because you can never end up with equal probability of losing and winning at the same time. And why is this? Actually, this is because the fundamental unit of calculation in quantum computers is something called qubit, or a quantum bit. And a qubit is a representation of all the different, or all the possible values between 0 and 1. So in classical information, the information is stored only in bits. So the information is either black or white. But in quantum computers, actually the information can be all in between. So it can be a combination of 0 and 1 at the same time. And it can be stored in something called a qubit, and a qubit can be simulated on different things. It can be simulated on diamonds, on electrons, on photons, etc. So there is different representation of qubits. So we have the first representation, which is the bracket notation, or the Dirac notation, which is the representation that physicists like the most. The blue one is called the kit, and it represents actually the state where we are right now. And the red one is the bra, and it represents the state that we are going to measure, or the future state that we will be in. There is another representation of qubits. It's called the block sphere, and it's basically a visualization of the qubit. So you can see like the psi is the state of our qubit, and it is governed by two phases, the phase theta and the phase phi. And the last representation is the vector representation, which is like the representation that most of us are interested in as computer scientists. So you can represent actually a quantum information in a vector. So the state 1 is not only 1, like in the binary system, it can be written as a vector 0, 1. If you want to represent the state 0, and then it's going to be a vector of 1, 0. And actually, the state is written as equal probability of, or the probability alpha of being in state 0 plus the probability beta of being in state 1. So why is this and how these qubits actually work? So we have some phenomena that exist in quantum physics and that we inspired from them to create this this generation of quantum computers. The first one is the superposition. So the superposition is the fact that a particle or like a quantum particle can exist in multiple states at once. So you can imagine that if you're trying to play this game, like you're trying to escape a maze and you play this game on a classical and a quantum machine, even with the best classical machine that exists right now, you can never find the correct path to escape the maze in one shot. But if you play this game on a quantum computer, you put your maze in a superposition, and then once you do the measurements, actually all the wrong paths will interfere, will cancel out, and it will amplify the right solution that once you measure it, you will get in one measurement, one single shoot, the right path that will lead you out of the maze. So this is actually the power of superposition. And then we have the quantum uncertainty and quantum measurement. And we always refer to it by this example of the Schrödinger's cat. Actually, we're not killing any cats here, but it just is named after the scientist or the physicist who came up with the Schrödinger equation, which is a solution of Hamiltonians. So if we imagine that we put a cat in a box with a poison, as long as the box is closed, we actually don't know whether the cat is alive or dead. So it's actually in a superposition state of being alive and dead at the same time. So if we want to write the quantum state of this cat, it's actually equal to alpha of the cat being alive plus beta of the cat being dead. And once we open the box, we can measure, we can see the reality, and then we'll see the cat collapse into one state. It's going to be either like dead or alive, and nothing in between. And we call this actually the quantum measurement, because all the quantum information at the end can be a classical information, because we're going to measure it and we're going to use it as deterministic output. We have another exciting phenomena which is called quantum entanglement. And actually, particles, if they are governed by the same wave function, even if you put them far away, you still can control the information in two particles at the same time. There are a lot of videos that I can recommend for you that explains quantum entanglement really well. Well, we have also something called the quantum gates, similar to classical computers where we have many gates like XOR, NOR, etc. In quantum computing, we have something called quantum gates. These are the basic gates, and we have more complex gates. You can think of gates as only matrices, like very large matrices that you multiply your quantum states with these matrices, and you find different outputs and different results. So the first gate is called the Hadamard gate that allows us to put two qubits in a superposition. Means that these two qubits, they have equal probabilities. We have the qubit flip, or the X gate, which allow us to flip the state of the qubit from 0 to 1 and from 1 to 0. We have the rotational gates. They are called RZ, RX, and RY, because we can actually rotate the state of the qubit on the Bloch sphere, and you see like the Bloch sphere is a 3D representation of the quantum state. And this is a way of how we can encode classical information into quantum information. And this is what we use exactly in quantum machine learning if we want to encode our classical data into quantum data. And then we have the entanglement gate, which allow us to put two qubits in entanglement state. We also have the Bell state, which is really known, and it actually creates a perfect superposition or perfect correlation between two qubits, where these qubits can be in a superposition and also can be entangled. We have the swap gates as well, and the swap gates, they allow us to swap the position of qubits in a quantum circuit. Does this make sense? Okay, I think it's fine, because Richard Feynman, who's the father of quantum mechanics, says that if you think you understand quantum mechanics, you don't understand quantum mechanics. So if you understood at least 10% of what I presented before, that's good. You can follow up with the rest of the presentation. Yeah, so let's talk about the real hardware in quantum computing. Only between 2023 and 2025, we saw this explosion of a lot of companies presenting their hardware, claiming quantum advantage. We solved this very hard problem that a classical computer cannot solve in 25 million years in only a few seconds. So we had companies like IBM, Google, D-Wave, Amazon, Microsoft, and many, many more representing their quantum hardware. For IBM, they do have their Heron chip, which is the latest chip that is available or commercialized right now, which has around 156 qubits, and they are aiming to reach fault-tolerant quantum computing by 2029. We have Google Quantum AI with their 105 qubit chip, which is the most error-corrected superconducting chip that exists right now, thanks to people from Google DeepMind who used reinforcement learning to do quantum error correction on this chip. We have also D-Wave Quantum Annealer, which has around 5,000 qubits, actually. We're not only in 100 qubits, because D-Wave, they have a topological architecture of qubits. They are simulating quantum annealing on their hardware, so they have more qubits. Actually, only between 2024 and 2025, we had over 6,000 publications about quantum machine learning on arXiv. 35 to 40% of these publications are actually peer-reviewed, and many of them has been published in conferences like NeurIPS, for example. So there is a really real interest in quantum algorithms. Although we're a little bit far when we talk about hardware, but scientists are trying their best to come up with new ways to do quantum machine learning, leveraging these quantum phenomena. So the director of Berkeley Lab, Bert DeJean, he said, AI will be used to design the next generation of quantum technology and be incorporated into programming, controlling, and error-correcting quantum computers. And that's why we need AI in quantum computing, and also we need quantum computing in AI. So if we want to know what is quantum machine learning, actually in the literature there are different definitions of quantum machine learning, and scientists are exploring it in different approaches. One of them is the intersection of classical machine learning with quantum computing, and the other one is actually leveraging the real quantum phenomena in quantum computing in order to do machine learning more effectively. So with the hype, AI is a hype and quantum computing is a hype, and now we have the hype of quantum AI. So people are publishing like crazy in different conferences and different venues about some random experiments of mixing both, like quantum with AI. But we do have some challenges in quantum or classical machine learning that we are hopeful that we have a quantum advantage if we leverage quantum correctly to solve these problems. The first one is the large feature space in classical machine learning. So the fact that we can put our quantum data in superposition, we can explore these large feature spaces really quickly. And actually, there was a poster presentation here by a student from Saudi Arabia, and she worked on a project on how to compress the number of features to train a quantum, a classical model using quantum computing. We also have the problem of high-dimensional data, and in quantum computing, we can actually train our models with less data, and we can still have the same accuracy, the same precision, etc. We also have very slow kernel evaluation methods in classical computing, and there are alternatives in quantum computing, like algorithms called the quantum kernel methods, which are more faster and secure. And then for the non-convex optimization problem, we do have other variants of optimization algorithms that are inspired from quantum computing, for example, quantum annealing, quantum approximate optimization algorithm, and variational quantum solvers, which can be used actually to optimize quantum models. There are several applications, so there are some algorithms that exist and that actually prove that there is a potential for quantum advantage using quantum computing. One of them is called the Grover's algorithm, which allow us to search in unstructured data sets with a complexity of O square of root of n instead of On. We also have the Shor's algorithm, which can allow us to factorize any prime number, no matter how big is it, in a polynomial time. And this is actually used in cybersecurity and the new generation of quantum cryptography. We also have the like the memory saving. So imagine if you want to encode a picture of 1024 by 1024 pixels, you will need around or more than 1 million bits. But if you do this using like the amplitude encoding on a quantum computer, you will be able to do that in around 20 bits, or like with 20 bits only. And the question that we ask, are we doing quantum machine learning right? Are we investing like in the right direction if classical machine learning is doing great? Actually, there are several approaches that we can do machine learning with AI. One of them is the quantum enhanced machine learning, where we have like some variants of the same machine learning algorithms that exist in classical computing, but these are like the quantum versions of it. We have, for example, quantum neural networks, quantum GANs, quantum like k-mean clustering, and many, many other examples. We have the second approach, which is the hybrid models, where scientists tend to, for example, encode the data using quantum algorithms and then use this data, like this large feature space, that they can extract easily on classical model. Or, for example, creates like a hybrid model where some of the layers are quantum, and some of the layers are classical, and then use a classical optimizer in order to train the model. Then we have classical machine learning for quantum tasks, so we can use like classical machine learning, like reinforcement learning, or just like machine learning to predict the output of quantum circuits, to optimize circuits, to actually control the error, do error mitigation on quantum computers. And we have the last category, which I invented. It's called clever quantum machine learning algorithm. And these are like algorithms that are really inspired from the quantum phenomena, and they always play on the complexity of the algorithm, how far you can make your algorithm complex, like the Grover search or like the Shor's algorithm, so that you can actually leverage the advantage of quantum computers. There are many, for example, the quantum Hadamard edge detection that can allow you to actually calculate the gradient with a complexity of O1 instead of ON. It's completely independent of the number of parameters that you have in your model, and this is actually magic for AI. There is this cool example of GPT on a quantum computer. So these are a couple of scientists that tried to create a version of GPT-3 on a quantum computer, and they claim that the training data, which has around 175 million parameters, can be actually encoded on 38 qubits, but this is far from reality because we do have to correct these qubits. There are several use cases. For example, we can use quantum combinatorial reasoning to train LLMs to work better. We have, for example, quantum edge detection to be able to construct or like to extract features more efficiently from high-resolutional pictures. We have QML algorithms that can allow us to predict molecules' properties. We have many examples. We have quantum NLP, which is completely different than the classical NLP, where you use something called the CCG grammar in order to encode your text into quantum states. Okay, so when we talk about error correction, there is like this cool framework that has been developed by Google DeepMind and Google Quantum AI that actually leverage reinforcement learning to do error correction. And this is actually the state of the art right now in error correction because they reached below threshold. So there is a lot of limitation in quantum machine learning. For now, there is like the problem of the barren plateau. If your circuit is really deep, you can have the problem of the vanishing gradient. And we have also other problems in the data because we actually cannot hold the quantum state for more than 13 seconds, which makes data encoding in quantum really, really hard. There are several types and modalities of quantum computers. So there is no universal computer, but there are several types. For example, we have superconducting quantum computers, similar to the one of IBM, IBM and Google. We have the trapped ion quantum computers, similar to the one of Microsoft. We have photonic quantum computers, quantum annealers, and many, many other modalities. And actually, if you think about it, we do have a standardized way. It's actually similar to the assembly language, where you can write all of your quantum codes as an open chasm, like the fourth picture, and you can run it on any of these hardwares. So actually, the number of qubits is no longer 100. For example, in Caltech University, there is this quantum computer that they have, and it has 6,000 qubits, and they are really high fidelity qubits that they are using in their research. So they maintain the superposition for approximately 13 seconds, which is really great. In Denmark, for example, we have this MenaML quantum computer that has been installed 3 days ago, and it's like the largest quantum computer in terms of logical qubits. So it has 50 logical qubits and around 1,200 physical qubits. It's developed by Atom Quantum Computing and Microsoft. NVIDIA as well is incorporating its super computers with quantum computing. So they have two frameworks that are open source and that you can use them. The first one is the CUDA-Q for error correction, and the second one is the CUDA-Q solver that allow you to solve a lot of complex problems. We have actually a hot area in quantum computing right now, which is the area that I'm also doing my research in. It's called distributed quantum computing. It answers the question of how can we actually distribute a quantum program on different modalities, multi-chip modalities, and also different GPUs and CPUs. How can we leverage this power of the two computers at the same time? I'm going so quick. I don't have a lot of time, but I have a lot of things to say. So this is an example of the IBM Quantum Data Center that is installed in Germany, and they are doing some great work. And just for your note, it's a fun fact that last year has been designed as the year of quantum science and technology because it marks 100 years since the quantum theorem has existed. And the Nobel Prize in Physics went to scientists that works in quantum computing. One of them is Michael Devore, who's a researcher at Google Quantum AI. Actually, there is a lot of good application. Quantum teleportation has been proven by Northeastern University in 2024. Our iMessage actually uses quantum encryption, and a lot of you doesn't know. iPhone users, you don't know that you're using quantum computing in your iPhones. There are a lot of applications at, for example, BMW and Mercedes using quantum computing to simulate the electrical batteries that they have. And I just want to answer the question of why I get into quantum computing. So I've been always fascinated by the quantum physics of space-time and how actually the black holes theory works, and how can we re-extract the information back from a black hole using a quantum computer. This has been my motivation to join in the field because my background is hybrid. I'm a computer scientist by nature, but I also did quantum information, and I sit in the intersection of the both. Yeah, so there is a lot of, actually these are two quantum computers that exist in reality. These are Chinese quantum computers. The one in the middle has 2 qubits, and they use it in China to teach students in high school about quantum computing. The other one on the left is it's a processing unit of quantum computing. See, so we can see actually a quantum computer in front of our eyes, and it's actually working, and you can use it and manipulate all the gates. Yeah, so just to talk, I still have 2 slides. So just to talk a little bit about the ecosystem of quantum computing. So like before arriving here at Coast, I saw this announcement of creating the quantum foundry for developing quantum hardware at Coast, which is a great initiative, but we already have many universities in the Middle East or in North Africa that are doing quantum computing. One of them is New York University of Abu Dhabi, QC2 Center in Qatar, and the TII Technology Innovation Institute that have like a lot of applications for quantum computing. They also have a small quantum computer in their lab. Yeah, so I just want to talk to you a little bit about Quantum Africa. So Quantum Africa is a foundation and an NGO that we created 3 years ago, almost 3 years ago, now it's like 2 years. But we have actually more than 270 members, and we're doing quantum education in several parts of the continent. Now we have almost 9 chapters and people from 38 countries. We're present in most of the quantum conferences. We do workshops about quantum machine learning and quantum technology, etc. We've been present in several events. We hosted many hackathons for students to learn about quantum computing. We recently had the Pan-African Quantum Challenge, which had more than 1,000 participants from all over Africa. And yeah, so thank you so much. Hope you enjoyed the talk. Yeah, I've been very fast explaining some of the details. So the field is really complex, but I hope that you at least got 30% of my presentation. I would be really, really happy. I would love to have one question. Okay, one question.
Thank you, Yousra, for the great talk. And okay, only one, right? Then I have to choose. Is quantum gonna break all cryptography algorithms that secure us at the moment?
Okay, that's a good question because as long as we do have the short algorithm that can break any prime number, a lot of science. So there is a research that has been published in 2025 by a group of scientists in Japan and China. They were able to break the RSA 28 bits using D-Wave quantum computer. So theoretically speaking, yes, but hardware-wise, we're a little bit far away from this reality.
Okay,
yeah. And that's why actually 3 years ago there has been standardized the NIST, which is like the standards for quantum cryptography, and now they are like doing some sort of education for all countries to adapt the NIST or the new standards for quantum cryptography and quantum security in general. In China they did this 5 years ago, but in the US and other like powerful countries they started doing this since like 2 or 3 years ago. Yeah.
Mentioning the hardware. That's it?
You can have one more question,
okay.
I guess.
Okay,
yeah.
Perfect. So mentioning the hardware problem, like, how to solve the temperature issue to have this superposition possible more than 13 seconds? Is there like some open directions into that?
Yes, we actually have quantum error correction, which is right now used to stabilize the qubits so that we can have, so there is a theorem called the Niels theorem or the threshold theorem that says that we can actually get the quantum advantage with a low percentage of error in our qubits. So the qubits, they don't need to be 100% correct. They can be 70% correct, and then you still can show a little bit of quantum advantage. So it's a really open direction that you, as well in machine learning or reinforcement learning, can jump into it and work on quantum error correction.
Thank you.
Yes.
Yousra, thank you for your time and effort in the slide. My question is how to join to Africa Quantum. Is there any chance to join to the research group?
Yeah, I actually had like a QR code on one of the slides. I don't know if you can get back the slides, but like you can just Google Quantum Africa. You'll find a button that can take you to the registration link. You fill the form, and then we'll get back to you and inform you if you joined or not. But it's open as long as you want to learn about quantum computing. At least, yeah, it's open for everyone, and you can join. You're welcome. Actually, we have a lot of members who are not Africans, so you're all welcome to join.
Hi, Yousra.
Yes, hi.
Thank you for your presentation. I had a quick question regarding one of your slides. You're saying that with, I guess, quantum-empowered computation, you can explore states all at once. And I feel like there's a bit of a theoretical disconnect because it kind of suggests that you would have something like NP or co-NP being equal to
yes.
like bounded quantum computation, whatever that class is called.
Yes.
And I don't think that is correct necessarily. So, like, is there one more nuance to you can explore all states, or?
We still haven't resolved the P equal to MP on a quantum computer. It's still an open question in mathematics. But there is a paper that has been published in late 2024 that shows that it is possible to solve NP-hard problems on quantum computers, but we still don't know whether these NP-hard problems can interfere with the BQP. So it's kind of open. So we still don't have an answer right now if we can solve exactly NP-hard optimization problems using quantum computers. Although using quantum annealing, you can get to the most optimal solution or the near most optimal solution for your NP-hard optimization problem with less time, well, with like few seconds, less resources. And this is like an area called quantum optimization. They're doing a lot of work in this area.
I guess a small nitpick,
Yes.
like NP optimization problem kind of doesn't type check? Because we're talking about decision problems. So you're more like a yes, no kind of question?
You're talking about BQP problems, because these are the problems that we can solve. Like, we aim to solve if we have the full potential advantage on a quantum computer, but we cannot say that we can solve them right now on a quantum computer. These are the bounded problems.
So what does it mean to explore all states?
Exploring all states is the fact that if you create your Hamiltonian and you try to put all the particles in a superposition, you're actually one particle can exist in multiple states. So if you want to measure it, whenever you do one-shot measurement, you get a new state. So the superposition is a state that is like a transition state, you can imagine it. And once you do the measurement, it's all deterministic. It's all like it collapsed to one classical state. So the superposition is just like